everyone. In the previous class, we learnt about multiple layers of the beams or the layers when we excavate in laminated rocks. So, we first saw that how the two layers or two beams can be analyzed, and then we extended or made it more generalized situation in case if you have say n number of layers which are participating in the deflection. So, in that case we took the theory of beams to analyze such type of underground excavations in laminated rocks. I mentioned to you that based upon the aspect ratio of the opening, either you have to use the theory of beams or theory of plates. So, today we are going to discuss those cases where there is going to be biaxial bending in the roof portion, and therefore, one has to go for the use of theory of plates for the analysis of opening in laminated rocks. So, let us try to take a look that the cases of caverns where you have W by B or L by B is less than or equal to 2:1. We all know that B is the dimension perpendicular to the plane of the screen and W is the width of the opening. So, in case if the aspect ratio is such that W by B is less than or equal to 2:1, which is in case of caverns, in that case the immediate roof acts as a rectangular plate which is subjected to biaxial bending. That means that the bending will happen in both the direction, in this direction as well as in this direction, and therefore one cannot use the theory of beams for the analysis because it becomes a 3D situation. So, one needs to go for the theory of plates while analyzing the openings having this W by B less than or equal to 2:1. And in this case, the maximum deflection of the immediate roof in the condition of biaxial bending would be given by delta max is equal to alpha gamma W to the power 4 divided by E T square, where this WB, the shorter lateral dimension of the excavation, and the maximum stress that can be given by sigma max to be equal to 6 beta gamma W square by T, and this is going to occur at the center of larger dimension, where this T be the thickness of the immediate roof, and alpha and beta, these are the function of B by W. So, this is how the maximum deflection and the maximum stress can be obtained. The question comes, what should be the value of these alpha and beta? So, the for the rectangular roof which is carrying the uniformly distributed load for various ratios of B by W, values of alpha and beta, they are tabulated here. So, in case if you have as the ratio as 1, then alpha is 0.0138 and beta is 0.0513, and this beta increases to 0.0833 when B by W tends to infinity. Similarly, this alpha increases to 0.0284 for the ratio B by W tending to infinity. Now, if we define this R naught as the modulus of rupture, which is the outer fiber tensile strength, then your sigma max is equal to R naught upon the factor of safety, and therefore the span width W can be written as square root of R naught into T divided by 6 beta gamma into factor of safety Fs. So, this is how the span width is obtained in case of the roof acting as a plate or experiencing biaxial bending. Now, as of now, we have discussed only the horizontal layers as a part of roof, but then there can always be the occurrence of the inclined roof. So, let us take a look that how can we handle such situation. There can be two types of roof where we can have two situation. First is that the long axis of the roof is inclined and short axis is horizontal. So, take a look, let us say if this is the long axis and this is what is the short axis. So, the situation is going to be like this. So, this short axis which is horizontal, but the long axis is inclined. So, this is how it looks like in plan, and in the section AA if you see, this is how it will look like, where this theta gives me the inclination of the long axis with the horizontal. However, there can be another situation where the long axis is horizontal and the short axis is inclined. This means it is like this. So, you see the long axis is horizontal, it is not inclined, but the short axis is inclined. So, this is how it looks in plan, and if you just take a section BB, it will look like this as part of case 2. Now, each type of roof, whether it is type 1 or type 2, the angle that is measured between roof and the horizontal, we are designating it by theta, and the assumption that is involved here is that the stress in the roof layer is due to the flexure which is caused by gravity. There are no external forces except for the force by gravity. So, for either type of the situation, the maximum stress is given by sigma max to be equal to gamma W square by 2t cos of theta. Now, this is there for W by B greater than 2:1, and since this is the situation, what we are going to use is beam theory. And hence, the design span width can be given as square root of 2t upon gamma cos of theta into sigma max, or I can write in terms of modulus of rupture, that is going to be square root of 2t r naught divided by gamma factor of safety into cos of theta. So, this is how we are going to obtain the design span width in case if we have the inclined roof, and this is for the situation when you have W by B more than 2:1. Now, as this theta increases, that means the inclination of the layers or the beams they increase, the behavior of the roof will create problem depending upon the mobilization of shear along the lamina plane. See how it will look like. the situation is going to be something like this. So here you have the opening, and here there are the planes of weakness. So there is going to be the mobilization of shear along these planes. This angle is theta. So just imagine what will happen as theta increases. This is going to have the problem. The roof is going to have the problem. Since the bond is strength in across the direction, it will cause the failure because of the tensile in nature. Now coming to the openings which have the planes of weakness which are not parallel to roof. So we can have the underground excavation divided into two parts or two categories, I should say. The first one corresponds to the mining activities in stratified deposits. There can be mineralization in beds, and other category belongs to the tunnels or caverns for other purposes such as hydroelectric projects, strategic installation. Now, in case if we have the first situation, that is mining activities in stratified deposits, these are rarely circular and generally square or rectangular in cross section. However, in the case of the tunnels and caverns which belong to the other category of the underground excavation, we have the operational considerations which govern the shape of the opening. So please remember that these two are the distinct main categories as far as underground excavations are concerned. In case if you have the mining activities in stratified deposits, they are rarely circular, usually they are square and rectangle in cross section. However, in case of the tunnels or caverns which are used for the hydroelectric projects, there the operational considerations are the ones which govern the shape of the opening, whether circular, elliptical, ovaloidal or square or rectangular or any other shape. So that is what is the difference. Now, in case if you have the mining activity, so I mentioned that these are rarely circular but generally square and rectangle in cross section. So, there will have the roof or the floor, and these can be either horizontal or inclined. Now, in case if they are inclined, the roof of the cavity is excavated parallel to the plane of weakness. Take a look how. So you see here this is inclined. So what we do is we have the excavation in such a manner that the roof is parallel to the planes of weakness. So this is how we go for the opening in rocks which have the planes of weakness not parallel to roof, especially in case of the mining consideration. But in case if you have the situation where operational considerations are governing the shape of the opening, in that case the roof of the cavity has to be maintained horizontal because it is the operational consideration. So in such cases, what will happen is that the laminations will intersect the roof or the side wall. See how it looks like. Now say here I have the opening like this. So, its roof is to be horizontal, and you have the planes of weakness like this. And say if you have say this the third direction, so maybe this is x x, and here this is z z, and you have the y y axis here. There is going to be the mobilization of the shear stresses all along the plane of weakness like this. So, how to handle such situation? So, in this case the behavior of the stratified or laminated rock in roof governs the design, and it is the function of attitude of the planes of weakness, or also called as a dip. Then the in situ shear strength of the stratified or laminated or foliated rock along the plane of weakness is another governing factor, plus the bond strength across the plane of weakness. So, these are basically the three parameters which govern the design of the excavation where the roof is not parallel to the laminations. Now, the bond strength in tension is 0, especially if there is the soft gauge material along the planes of weakness, but this can be very high if there is the existence of a cementitious product along the planes of weakness, and it can be as high as that it can become even greater than the strength of the non-laminated rocks. So, one needs to be careful here as well. Coming to the aspect of stability for the openings in rock containing planes of weakness which are not parallel to the roof, you can have the three different cases. So, we have the first case, then case 2, and you have case 3. So, here I have elaborated each of these cases, but then in subsequent slides we will learn each case in detail one by one. So, as far as the case 1 is concerned, here of course the plane of weakness is an inclined plane having the characteristic as that its dip is going to be alpha degree with respect to horizontal, which is the y axis of the cross section, as I just now mentioned in the previous figure. Then the strike of these planes, they are parallel to the longitudinal axis of the cavity, that is the x axis. In case 2, again the plane of weakness is an inclined plane. So, basically here we are dealing with all the three cases where the plane of weakness is always an inclined plane, but its inclination is different in all the three cases, and accordingly we have defined these cases. So, the dip is going to be beta degree with respect to the longitudinal axis of the cavity, which is the x axis, and the strike is perpendicular to longitudinal axis. When I show you these cases with the help of figures, it will become more clear. In case 3, the dip is the vertical direction and the strike is gamma degree with respect to the longitudinal axis, which is x axis. Now, in the next slide, I have put the three figures showing various three cases. So, this is what is your case 1, this is case 2, and this is the situation case 3. So, you see that as I explained, the case 1 dip is alpha degree, in case of case 2 it was beta, in case of the third situation the dip is vertical, and you have this gamma degree here which is coming into picture. Let us understand these one by one with reference to first case. Again, I have reproduced the same thing, but with the help of the figure. Let us try to understand. Of course, the planes of weakness, they are inclined, no more horizontal with respect to roof, of course. Dip is alpha degree with respect to the horizontal axis of the cross section. So, you see that this is what is the horizontal axis, which is YY, and with respect to this the dip is alpha degree. The strike is parallel to the longitudinal axis of the cavity. So, the longitudinal axis of the cavity is what? Here it is XX. Now, the strike direction is what? Where the plane cuts the horizontal plane. So, you see that if you just take the look, then this will become parallel to this longitudinal axis. Now, there can be various situations based upon the range of the value of this angle alpha. Accordingly, you will have to take care of the opening and the corresponding support system. Let us take the first case, that is when alpha equal to 0 degree. We have the horizontal plane of weakness. You see that if this alpha becomes equal to 0, what we will have is the horizontal plane of weakness. And in that case, we will go back and use the beam or plate theory for the analysis of underground excavations, and accordingly once we know the maximum deflection, bending moment and shear force, accordingly we can design the underground excavation. Stress concentration and compressive strength of the rock in the side walls can be treated as if the rock were isotropic, in case if you have the situation when alpha is equal to 0 degree. Now, this alpha can take other values like more than 0. So, we have divided these in 3 different ranges, like when alpha equal to 0, alpha varying between 20 to 70 degree and alpha being more than 70 degree. So, depending upon the value of alpha, accordingly you will have to decide that how should we go about the analysis of the opening and subsequent design. Further, not only for the roof but for the side walls also, we have to see, depending upon the inclination of these planes of weakness, we have to assign the support system or design the support system. So, remaining different values of alpha for case 1 along with case 2 and case 3, that we will learn in the next class. Thank you very much.